Concrete is the most widely used construction material in the world, forming the backbone of modern infrastructure, from roads and bridges to buildings and dams. However, concrete is prone to cracking over time due to various factors such as environmental stress, thermal expansion, and mechanical loads. These cracks, if left untreated, can lead to structural failures and require costly repairs. Self-healing concrete is engineered to repair itself autonomously when cracks appear. This innovative material contains special agents such as bacteria or microcapsules filled with healing agents that are activated by the presence of moisture or air. When a crack forms, these agents react and create a substance like calcium carbonate that fills the crack, effectively sealing it and preventing further damage. There are different types of self-healing concrete. Bacteria-based self-healing concrete contains dormant bacteria like bacillus and a food source such as calcium lactate. When water enters through cracks, the bacteria activate and produce limestone, filling the cracks. Microcapsule-based self-healing concrete uses tiny capsules filled with healing agents like epoxy or other polymers. When a crack occurs, the capsules break open, releasing the agents to seal the cracks. Polymer-based self-healing concrete incorporates polymers that expand upon exposure to air or water, closing the cracks. Self-healing concrete is no longer just a concept. It is being tested and, in some cases, actively used across various industries and infrastructures around the world. Here are some of the key areas where self-healing concrete is making an impact. On civil infrastructure projects, bridges and tunnels. The Dutch government has been a pioneer in applying self-healing concrete technology in infrastructure. In the Netherlands, self-healing concrete was used in the construction of a small-scale pedestrian bridge in the city of Nijmegen. The bridge incorporated bacteria-based self-healing concrete to prevent water seepage and reduce maintenance costs over its lifetime. Roadways. In the UK, the University of Cambridge and other institutions have been conducting trials on self-healing concrete for road applications. By embedding microcapsules of healing agents within the road surface, the material can repair small cracks caused by heavy traffic loads and temperature variations, potentially extending the lifespan of roads and reducing the need for frequent repairs. Commercial and residential buildings are increasingly looking to self-healing concrete for enhanced durability. In France, Bouygues Construction has tested this innovative material in new building foundations and walls. This approach is especially beneficial for structures exposed to harsh environmental elements like coastal buildings where salt water and humidity can speed up concrete degradation. Parking garages, too, are seeing the benefits. These structures endure heavy vehicular traffic and are often exposed to the elements, leading to frequent cracking and damage. In the United States, several pilot projects have utilized self-healing concrete in parking garages, aiming to minimize maintenance needs and improve structural integrity over time. Water infrastructure, such as dams and reservoirs, is another area where self-healing concrete is making significant strides. In South Korea, researchers have found that using self-healing concrete in dam construction can significantly reduce maintenance costs and extend the operational life of these critical infrastructures. Water treatment plants also face constant exposure to water and chemical agents that can degrade concrete structures. The incorporation of self-healing concrete in these facilities can prevent leaks, reduce downtime, and ensure the uninterrupted operation of essential public services. Marine and coastal structures are particularly vulnerable to saltwater corrosion and cracking due to constant exposure to harsh conditions. In Norway, self-healing concrete is being tested for seawalls and offshore platforms to reduce corrosion and extend the life of these structures. This innovation could save millions in repair and replacement costs while enhancing safety. Wind turbine foundations are subjected to high mechanical stresses and harsh environmental conditions. In Spain, self-healing concrete is being tested in wind turbine foundations to address cracking and prolong the lifespan of renewable energy infrastructure. Concrete plays a crucial role in the containment structures of nuclear power plants. Researchers are exploring the use of self-healing concrete to ensure the long-term durability and safety of these facilities, reducing the risk of radioactive leaks due to structural failures. Self-healing concrete offers several advantages, such as reduced maintenance costs by automatically repairing minor cracks, which extends the lifespan of structures and improves overall safety for critical infrastructure like bridges and dams. It also provides environmental benefits by lowering the carbon footprint associated with repairs and replacements. However, challenges remain, including the higher initial costs compared to traditional concrete, the need for further research to scale its use across diverse construction projects, and the requirement for long-term studies to validate its effectiveness in real-world conditions. Thank you for watching this video. I'll catch up with you in another exciting video soon. Until then, goodbye and take care.